Dr. Zhi-De Deng from NIMH. Zhi, are you with us?
I am. Can you hear me?
Yes, good morning. Go ahead.
You can see me as well. Okay, great. Thank you for inviting me for this panel. It's very interesting. The whole webinar and also last week's webinar was eye-opening as well. Today, I'm going to be talking about electric field modeling and using e-fields to optimize individualized targeting related to TMS and some TES applications as well. Next slide. As you well know, I think most of us on the panel generally agree, or maybe even universally agree, that current targeting approaches that are used for clinical TMS is considered suboptimal. The 5-centimeter rule does not account for individual variation in head anatomy or head size. And no matter how well you do it, even some systems provide laser guidance to measure this 5-centimeter quite precisely. It often selects spots that are outside of the DLPFC. Alternative approaches that are also based on scalp targeting, the so-called beam F3 method, does a little bit better because it's the EEG system scales for at least head size, and yet it is still a blinded approach in the sense that it does not account for cortical anatomy. More sophisticated targeting approaches include structural MRI-guided approaches to locate DLPFC target. And this is a study that I'm going to talk a little bit about. This was data collected at the Mayo Clinic from Dr. Paul Crokin in adolescents who were treated with TMS. And the localization, the TMS localization strategy uses a structural MRI to guide the coil placement. But in the same individuals, brain scans were also acquired with vitamin E capsules on the scalp, labeling the 5-centimeter targets and the F3 targets, as well as the ultimate treatment target, which was structurally guided. Next slide. This afforded us the, go back one more. Yes, this afforded us the opportunity to model TMS with the different treatment targets in the same individual and compare the electric field distribution. So these are individual adolescent patients, depressed patients who receive TMS to the left dorsolateral prefrontal cortex. And you can see a lot of variability in terms of where the targets ended up. And so when you summarize the electric field, next, in this plot here, you can see that the 5-centimeter rule generally underdose electric field to a structurally defined ROI for DLPFC. The F3 target generally does a little bit better in terms of raising the average electric field, but you can see even from this very small samples that there's a significant increase in the variability with the F3 strategy. Now I would like to talk about the last bar there, coded in purple. That is the computationally optimized coil location based on maximizing the electric field over your region of interest. And you can see that in all of the individuals, there is a substantial increase in the electric field. So so the electric field modeling technique can be used to maximize the dose in the brain. Next slide. The previously discussed method was quite general and could be done using fMRI as well. fMRI targeting, though, most of them do not consider the non-focal or off-target TMS effects or even account for large-scale connectivity patterns. This is work from Dr. Nick Balderston from University of Pennsylvania that attempts to integrate whole brain electric field and whole brain resting state functional connectivity to predict a treatment target for TMS. In this approach, first a PCA-based regression was done to predict symptoms from resting state functional connectivity, and this was done using some 91 anxious misery patients plus 25 control subjects. And the PCA will select out a number of components that account for some percentage of the variability in the functional connectivity signal as well as the clinical score. And in the second step, you would run electric field simulations and map the simulation onto a atlas, which is then used as a weighting matrix that modifies the functional connectivity. And in the third step, you can then systematically examine different coil locations as well as orientations that would modify the functional connectivity in such a way that in the feature space also produce a maximal change in in the clinical symptoms. So here on the right, I'm showing you heat maps from individual subjects and the optimization grid space. The colors represent the predicted depression score following a hypothetical course of TMS treatment to the left and right DLPFC. And you can see that the cool spots in the heat map are the TMS site and orientation that would yield maximum predicted symptom reduction. And in the anxious misery patients, the model predicted a significant decrease in the depression score for sites near the Brodmann area 9, but not over the motor cortex. In the control subjects that we looked at using this method, there was no site and orientation combination that showed a significant predicted change in depressive symptoms. Next slide. Yeah, so finally, I would like to talk about some more recent developments on the electric field modeling technique itself. First, these finite element models that we use to generate these electric field models, they're very computationally intensive, and we need to also consider the accuracy of these models. And so here are some recent work improving both the speed and accuracy of the E-field models, starting with the work on the left, led by Dr. Hongming Li and Yong Fan at University of Pennsylvania, using a deep learning approach to predict the electric field. And in this deep learning model, it is built to minimize an energy function that solves with a governing equation with boundary conditions. And so you can see the UNet encoder-decoder-like architecture of this model that allows you to estimate the electric field in a very rapid fashion. You can solve for one of these models in under a fraction of a second, much faster than the traditional way of solving the finite element equations. On the right, we consider the effect of better segmentation on the resultant electric field. So for example, in the tools that we use today that it's built into SimNibs or ROAST, it does not consider very fine geometry in the brain, such as the meninges. And so in this recent publication from Konstantin Weisse and Sergei Makarov, they examined the introduction of these finer structures, the dura, the pia matters, and their influence on the electric field. And it is shown in this work that for certain stimulation conditions, such as focal TES, inclusion of meninges in the brain in these electric field models substantially changes the electric field. And so in going forward, maybe these optimizations and more detailed, accurate, faster simulation methods can be incorporated into our daily routine to further optimize treatment dose. Thank you.
Thank you very much. Thank you very much.